Let's talk about a particular kind of differentiation when you've got some difficult problems to differentiate, and you can use some properties of logarithms to help. So this is called logarithmic differentiation. It's a mouthful. Here's what we're going to do. We are going to take a problem that looks kind of complicated. So take a problem, f of x. So we're given f of x. Usually it has a whole bunch of products and quotients and stuff like that in it. And we are going to take the log of both sides. So take the ln of both sides. Natural log. Then, so this is step 1, this is step 2. Step 3 would be differentiate both sides. Now I'm going to say with respect to x, so find dx, with respect to x, you may have a different variable. And then finally, solve for dy dx. All right? So that's what we're planning to do. Now, this may seem like it's got a lot of work, but compared to using a lot of quotients and products, it's going to be a little easier. I'll show you both examples. Here's my example that I want to use. So suppose I've got f of x, or y, is equal to x times the square root of x squared plus 1. Now this one's not terribly involved, but it's a good example to start with. So let me show you the traditional method. So traditional f prime of x. This is a product. So if I do the traditional f prime of x, I get this. I get f prime of x is equal to, okay, here's my f and here's my g. So f prime is 1 multiplied by g plus f left alone and then g prime. Well, this is x squared plus 1 to the 1/2. So I've got 1/2 x squared plus 1 to the minus 1/2, 1/2 minus 1, and then multiplied by the derivative of the inside, which is 2x. So traditionally, that's not the hardest problem in the world. I have not simplified anything. If I do simplify, it looks a little bit better, maybe. It's x squared plus 1 from this. Here I've got 2 and 2 canceling. I've got x times x, so I've got plus x squared, and this is a negative exponent, negative 1/2, so this is x squared plus 1. So there's the traditional method. Now, logarithmic differentiation. And you may not like this, but you can certainly use it, and sometimes you have to. You would not have to on this, obviously. But if I want to do logarithmic differentiation, I need to take the log of both sides. Now I'm going to call this y to make it easier to look at. So I'm going to say f of x equals y equals x square root of x squared plus 1. So then I take the log of both sides. Log of y is equal to the log of x times the square root of x squared plus 1. Now there are log properties. I probably should have put a step 2.5 here because there are log properties. And the reason that I'm doing logarithmic differentiation is because of the log properties. Got multiplication. Log of a multiplication, you add the logs. So got this one. So I just split it up at the product level and add the logs. Well, now this is to a power, so this is the log of x plus 1/2, that's the power, the log, let me just write that, x squared plus 1. So that's the log of y. So we have actually taken care of some things. Now, this says differentiate both sides. I've got to be careful because I have to differentiate this side. D dx. So derivative of a log is 1 over y times the derivative of y, which is dy dx. So 1 over is the derivative, and then you've got to take the derivative of the inside, and we're differentiating with respect to x, dx. So that's the challenging part. What's the derivative of ln x? It is 1 over x. That part's easy. Then we've got plus 1/2. Then we've got another log. So the derivative of a log function is 1 over, got x squared plus 1, then times the derivative of the inside, which is 2x in this case. So now here's what we have. We have 1 over y dy dx. So 1 over y dy dx is equal to 1 over x plus, I can cancel that, I've got x over x squared plus 1. But that's not the entire answer because I don't have dy dx solved. So let me multiply both sides by y. But what's y equal to? Well, y is equal to this. So this becomes 1 over x plus x over x squared plus 1 multiplied by x square root of x squared plus 1. Or if I simplify, I get 1 over x times this, which cancels the x's, plus, now this one, got x squared plus 1, and then I've got a half of a power of it, so I'm going to just take half a power out, cancel it, x times x is x squared. Okay. Notice this one and this one. They are identical. So you can use logarithmic differentiation and not use the product and quotient rules as much. Let's try a couple more examples of this just to get you used to it. So my next example is pretty hairy. It's got this. It's got y is equal to x plus 1 times x minus 2 over, so this example, x minus 1 and x plus 2. X is greater than 2. I'm going to take the log of both sides, and I'm going to simplify. So I've got the log of y is equal to, now this is going to be the log of this thing. These are multiplied, so this is the log of x plus 1, x minus 2, x minus 1, x plus 2. Notice with the problem set up that this is greater than 2, so I can legitimately take the log. Let me use log properties. This is the log of x plus 1 plus the log of x minus 2. Those are the two numerator parts. Then minus, and I've got a whole package of items, the log of x minus 1. This was multiplied, and I'm subtracting the whole thing, so minus the ln of x plus 2. So now I've got it all split up. I'm going to take the derivative. 1 over y dy dx is equal to, then the derivative of this, 1 over x plus 1. Derivative of x plus 1 is 1, plus 1 over x minus 2 times the derivative of x minus 2, that's 1, minus this one, minus 1 over x minus 1, derivative of x minus 1 is 1. I've got another minus, okay, this was a plus, wasn't it, because those were multiplied, so it turns out to be a minus. 1 over x plus 2, derivative of x plus 2 is just 1. So to get the answer now, I've got dy dx is equal to all this, and I don't need a common denominator for it necessarily. So I've got this, x minus 2 in the denominator, minus 1 over x minus 1, minus 1 over x plus 2, all packaged together multiplied by y. Well, times y, this is y, so it's times x plus 1, x minus 2 over x minus 1, x plus 2. And we're done with a problem that had two product rules and a quotient rule, and it was a whole lot faster. So sometimes logarithmic differentiation makes things a lot easier.